Hello, everyone. Welcome along to what is going to be a really, really exciting day of science communication content. My name is Sam Langford. I am, wherever you're watching this, I don't know where you're watching it on. You might be watching it on the Global Science Show account. You might be watching it on my personal account. I am Sam Langford. I am a science communicator based in Glasgow in Scotland. And over the course of today, we've got three incredible shows for you, which are all raising money for the RNLI, the Royal National Lifeboat Institution, which is an incredible charity and organisation based in the UK that saves lives at sea and tries to educate people on how to protect themselves at sea. And it's never been more important for us to support a charity like this when we have refugees trying to make their way to the United Kingdom and being met with huge barriers by, let's face it, a racist UK government. So supporting charities that help to support these people who are in the worst of conditions, dire straits, and need support. And so the charities need support as well. So throughout, there's going to be a chance to donate. Please do if you can. I'm going to disappear from your screens in just a second. You're not going to hear from me for an hour. You'll be glad to know. You're going to hear from two amazing science communicators who have a show for you called Big and Small. And I'm going to get them on screen just now. So say hello to Alex and Affelia. Hello, how are you doing?
Hello, we're good. Excited.
Yeah, hiya.
Awesome. I'm going to take up no more of your time. I'm going to disappear off. I'm going to pass over to you to get on with your show. Good luck. It's going to be awesome. Enjoy, folks.
Thank you.
So, hi, I'm Affelia.
And I'm Alex.
And welcome to Big and Small.
So we'll start by talking about arguments and what they're good for. You might be thinking not very much. It's quite a nightmare having to go back and forth over parking spaces with your neighbours or letting your boss know that a meeting really actually just could have been an email.
And well, in science, we actually have a slightly different approach to arguments. We kind of like them, not only because we like to be right and to prove ourselves, but arguments and disagreements between scientists is one of the ways that discoveries are made and how the field progresses. And we have some examples for you.
Yeah, so I'm going to take the first example, and that is Salk and Sabin. So these are two scientists that were working in the last century on something we've all heard an awful lot about recently, and that is vaccines. Now, these two managed to get quite a few jabs in at each other. Salk would fire some shots at Sabin about his work, and then Sabin would give Salk a dose of his own medicine. But at the end of the day, these two really worked to produce a polio vaccine and provide a huge booster to the vaccine community and save children's lives.
Have you heard of Edison and Tesla? So these two fellows were alive in the last century and they had a shocking argument about electricity, mostly about which one was better, alternating current or direct current. Not only did this charged rivalry transform society, but they also came up with some current inventions like the radio, the microphone, the remote control, and light bulbs as well. Now, I think they were trying to amp up what they could do.
Now I'm going to finish off this set of examples with something slightly more contemporary. There's one thing that we can all remember 2020 and 2021 for, right? Yep, it's the billionaire space race. Now, Jeff Bezos, Richard Branson, Elon Musk all went head to head to see who would be first to have the rich experience of being in space. And they really just wanted to check this off their bucket list, I think, and not many bonds were forged during this time. And unfortunately, there weren't any cash landings during it either. But supposedly, they've contributed to making space travel more commercial.
And today, we need your help to settle another very important scientific argument. Which one's better, studying really big things or studying really small things? And your contenders are us, two PhD students, each learning about those things. And we are determined, with your help, to prove that we haven't wasted our lives.
So, in the purple corner, we have Affelia Wibisono. They're a planetary scientist fighting on behalf of the heavyweight planet of our solar system, Jupiter. I'm trying to work out how the biggest planet in our neighbourhood produces the most intense northern and southern X-ray aurora. Now, they've discovered X-rays from Uranus. They have thousands of planetarium shows under their belt, and they once walked into astronaut Tim Peake while half asleep.
Yep, Yep, I did. And in the yellow corner, we have Alex Holmes, a PhD student in biophysics and biochemistry, and she's fighting for the small side of science. Now, she's got a really great talent for saying long biological words like membrane pyrophosphatase. Is that right?
Membrane integral pyrophosphatase, yeah.
Okay, I was nearly there. She's also had a promotion up the Pint of Science team. She's basically in charge of all of Yorkshire now. And she's held on to a shred of dignity through it all as well.
It was a good intro. I'm not sure I have held on to that shred of dignity following this show, but maybe we need to properly introduce ourselves to this audience.
So I'm Affelia. Some people call me an astronomer, other people call me an astrophysicist, but I also identify as a planetary scientist and occasionally a space plasma physicist. But whatever you call me, I study Jupiter's aurora, or the northern and southern lights. Most of the planets in our solar system have some kind of auroral emissions, and they're caused by charged particles from the sun entering the atmosphere, interacting with the gases in the atmosphere, and then they glow and give off these natural light displays. But my work has shown that Jupiter's is slightly different. They're actually mostly caused by the charged particles from Io's volcanoes. Io is one of Jupiter's largest moons. On its surface, there are hundreds of active volcanoes, and they release 1,000 kilograms of material out into space every second. So Jupiter's aurora come in lots of different forms. They come in radio waves, infrared light, visible light, ultraviolet light, and my favorite, X-rays.
So I'm Alex. I'm a biophysicist or biochemist, which basically means I'm studying parts of biology that is so small we can't really use traditional biological techniques for them. We have to start using chemical techniques and physical techniques. And I'm really interested in proteins, and in particular membrane integral pyrophosphatases, which Affelia told you about earlier. But proteins are really, really important. They're the business end of biology. They're tools your cells use to do all their jobs. So pretty much everything your body does controlled by proteins. So at the moment, there's proteins in your ear responding to the sound of my voice and the vibrations coming out of your computer or phone towards you. There's also proteins in your brain sending signals, hopefully about how much better small is than big, although that remains to be seen throughout this. And my job is all around understanding what these proteins look like, how they work, how they do their jobs, how they move, and designing chemicals to see if we can change the way that they do all of these.
So now you know a bit more about us and about what we do. How is this battle going to work? Well, we're going to fight it out over 3 rounds. The first round, Battle of the Scopes, telescopes versus microscopes. Second round is the Pretty Pictures round. And finally, we have the Impact on Humanities round. And we're going to use Mentimeter to cover up your votes. So you can open up a new tab or use your phones, go to menti.com and use the code that is on the screen, 149508887. So the winner, the overall winner, is whoever wins the most number of rounds. And if you're watching this on catch up or demand, you can still try to vote. They won't be counted, but at least you won't be charged. But of course, please do donate to the RNLI.
So let's pivot over to Mentimeter, show you what's happening over there. So there seems to just be one person so far that's through to our screen there. Let's see if a couple more people can get on. So that's menti.com and 149508887. And once you're there, you should be able to see our logo, which is really beautiful, designed by me. Let's see if we can get a couple more people over. There's also a link that's just been put into the comment section that you might be able to use to get over there too. Let's see. Maybe we'll just have one person. This person will have to make all the deciding votes. That's fine. We'll give people slightly longer to do that. So www.menti.com, you might have to open up a new tab, get out your phone, and use the code 149508887. And we'll wait in suspense. Once you are onto Mentimeter though, you should be able to answer a quick question whether or not you've made it there. So 2 options, yes or no. Oh, We've got a couple not yet, which is slightly concerning when to be on Mentor Newton Answers question you have to really have got there. Might need to keep our eye on this audience, Affelia. Okay, great. So we've got 5 of you that are voting, so that's pretty good. That at least that's never going to be a tie, which is good. So I'll take you on to our next question. This is completely a practice. This has no bearing on who actually wins or loses the show. It's just to get your initial ideas. Do you think big's better? Do you think small's better? And you can change your mind throughout the show. Don't feel like you're tied into this now. Oh, so we're actually evens on this. We've got, oh no, 2 small and 1 for big.
Yes.
There we go.
Wait, what? No.
No,
Come on. Come on, big.
Sorry, Affelia.
Oh, yeah, okay. Okay.
That's
I
the
think this is going to be a very close battle, Alex.
I think so. There's like one decider, really.
Okay. Oh, come on.
But remember, you can change your mind throughout. Affelia might call your way back.
I do have a lot of good stuff to tell you, so I'm confident.
Yeah. Oh, it's getting even more even. Okay, well let's go over then to our slideshow and get round 1 started.
And that is the telescopes versus microscopes round.
So I know a tiny bit about astronomy, but I do know you have to use telescopes. And I can just imagine how boring that is. You have to go out in the dark, in the cold, and let's be honest, we're in the UK, so it's going to be in the rain as well. And just wait for the clouds to clear so that you can get a good view of Jupiter. And I bet you're such a slacker. If it's cloudy, you just take the night off, right?
No. I do use telescopes, but it doesn't work like that. So I don't need to worry about being out in the dark because while my telescopes are in space, and I don't need to worry about the weather because my telescopes are in space, and I don't need to worry about being out in the dark because, well, and in the cold because my telescopes are in space. And I don't just have access to one telescope either. I have a whole fleet of them. The one that I use the most is XMM Newton. This is the European Space Agency's flagship X-ray telescope. And not only do we use it to study Jupiter's aurora, we use it to look at exploding stars, faraway galaxies, and active black holes too. And XMM has been working for more than double its expected lifetime, and it's still going strong. We get pictures and videos of Jupiter's ultraviolet aurora with the Hubble Space Telescope. It's probably the most famous space telescope out there. A lot of the really cool and amazing pictures of space you'd see were taken by Hubble, and it's been doing that since long before Alex was born. Hisaki is a Japanese satellite, and it lets us monitor Jupiter's aurora and Io's volcanoes over long periods of time, so it can tell us if those volcanoes have been particularly active recently. And later this year, this summer, and early next year, we're hopefully going to use JWST and XMM Newton and Hubble to look at Uranus in 3 different types of light: X-rays, ultraviolet light, and infrared light as well. So JWST is the largest and most powerful telescope to ever be built and put into space. It's about as high as a 3-story building, and it's as long as a tennis court as well. And it's so sensitive, it can detect the heat of a bumblebee that's as far away as the moon is to the Earth. So that's like 380,000 kilometers away. And even though Juno isn't strictly speaking a telescope, it's an orbiter. It's got a suite of instruments on board that lets it measure its surroundings. I use it to sort of give us context to what XMM and the others are seeing. So Juno was launched in 2011, and it reached Jupiter in 2016. And unlike any of the other spacecraft that was sent to the outer solar system, Juno is powered by solar panels. These panels are pretty big. They're 3 by 9 meters, and they're much more efficient than the ones that you might have on your roofs, for example. So some of these instruments include a radio and waves plasma detector, 2 plasma and energetic particles detectors, 3 cameras as well. So one looks at the infrared, one looks at the ultraviolet, and the other looks at the visible light. And you might have seen some of those incredible pictures that Juno have taken of Jupiter as well. And Alex told me earlier it looks like a fidget spinner. It does, and it does spin like one too. And actually, this spinning helps to control the spacecraft. It's much easier to control it when it's spinning than if it was just staying still. And because its instruments are fixed on the spacecraft, the spinning helps to make sure that they get measurements from sort of all the way around. But what I think is really impressive is, well, one, it can let us see the invisible, but all of these space telescopes and these spacecraft need to work first time round. If something breaks or stops working, we can't send someone there to fix it. And just think about all the work and the engineering and the thought behind designing and building these things to make sure that they work in the harsh environments of space.
That is amazing. And it is a really lovely fidget spinner. I'm just thinking, if it has to live in the harsh realities of space, why even have them in space in the first place? Why not just keep on Earth where we can look after them?
So if we want to measure what's going on around Jupiter, we need to get to Jupiter. And in the case of XMM and Hubble and Hisaki and JWST in a sense of, we want to get away from the Earth's atmosphere. The Earth's atmosphere blocks out ultraviolet and X-ray light. It also makes things sort of fuzzy, and it's just not so good if we had these telescopes on the ground. Now, there is something I want to tell you, and that is a great sense of power I get when I know that these things are looking at Jupiter and Uranus. The reason is, well, it's me.
Oh, so you actually control them?
Well, no, not quite. The operations teams at the space agencies do, but I get to try and convince them that it's a good idea. And I don't know if I mentioned, Alex, but my telescopes are in space. Where are your microscopes?
Okay. Space is hard to beat, and my microscopes are next to a grotty car park in Leeds. But it doesn't take away how amazing they are. And have you ever used a microscope, Affelia?
Oh, I have actually. So when I was younger at school, we used them. I also had a horrible science microscope too. And I remember how fiddly it was to use. Like, you have to prepare the slides, you've got to make sure there aren't any scratches or air bubbles, and then you've got to focus the microscope and then draw what you see. It must be a pain having to do that again and again.
Those kind of microscopes do require a lot of steps. Slightly less than building a whole telescope and shooting it into space and never being able to check that it's properly working, but that's fine. But that's not the kind of microscope I actually want to tell you about, and it's not the kind that I think is going to get me votes this round. So instead of telling you about light microscopes, which we've used in school, I want to tell you about electron microscopes. And these let us see things far, far, far smaller than just cells. So I'm going to take you on a little bit of journey through scale to get to where I'm working. So we'll start with meters. This is what you might use to measure an entire person. Then we get down to centimeters, which is really good for things like organs. And yeah, sorry. And then we get down to millimeters, which is where we get individual blood vessels that we can measure. And then we get down into micrometers. Now, you might not have heard of this unit, but it's really good for measuring cells. They're around 100 micrometers across. But if you want to get even smaller, say 1,000 times smaller, we get down to nanometers, and this is where proteins are. So a protein, in comparison to a cell, the biggest proteins we have, they're about the size of a football in comparison to 8 football pitches being a cell. So an awful lot smaller. It's much harder to see them. And if you want to see them in any actual detail, we have to use quite a cool unit. It's called an angstrom. And this is about the length of a bond between 2 carbon atoms. So we're at a level of biology where we're literally looking at the chemicals, we're looking at the atoms and the bonds in between them, which is just magical that we have equipment that actually lets us do that. But this is kind of where we have to start using electrons rather than light. Light is actually quite big, even though you might not think about it as actually having a size. But it's so big, it's actually bigger than proteins. So they are literally invisible. And instead we have to use electrons. These have a smaller wavelength. And it's all to do with something called resolution. So the better resolution something is, the better detail we have, and that's to do with the pixel size. So here we have some huge pixels, really low resolution. But as the pixels get smaller, we get better and better resolution until we can make out what we're looking at. In this case, it's a slightly blurred version of our logo. So you can see how the size of the pixel really matters. And in the case of microscopes, it's the size of kind of the probe we're using, whether it's light or whether it's electrons. And not only that, we have to try and keep the sample still. So if anyone watching has children, if you ever try to take photos of them, you probably have a whole series of blurred pictures. I'm sure Sam taking photos of Prue, half of them are blurred because she's running about. So what we do is we flash freeze the proteins, get them super cold, they can't move, they're frozen in place. And that means we can get a really highly detailed picture. And that's all thanks to my microscopes.
So they are a bit like the ones we might use at school, but with electrons and maybe a bit colder?
A bit colder. I mean, it's all relative, but we're talking like minus 100 and like 96 degrees, which is a lot colder than you probably got in school. For context, the coldest we've ever measured thanks to the weather on Earth is minus 89 degrees. So just 100 degrees different.
Yeah, that's pretty cold, but space is colder.
Yeah,
Or
but you
parts of
don't
space are
control
colder.
space. Yeah, the bit outside the sun would definitely argue with you there. But you're not controlling it. Whereas these microscopes, we are controlling temperatures that are going into it and staying in it. And not just that they're colder, but they're also bigger. These are huge. So I have a photo of 1.5. I've managed to cut out half of one of them, but of the electron microscopes we have in Leeds, with my friend Connie as kind of a human ruler next to it. These are about 11 feet tall. Now, Aphelia's a bit short, so it's the equivalent of if they stood on top of my shoulders. That's how tall this is, pretty much. So massive, and it has all this padding, it has all this safety stuff. Like, these are really, really high-tech microscopes.
Okay. Okay, they are different to the ones that you might have used at school. But remember how cool my telescopes are as well. I mean, they're not the ones that you might get at Argos. Should we go to the Mentimeter?
Yeah, go on.
Right.
This is not sponsored by Argos, just to confirm.
My first telescope was from Argos. That's why I said it.
Oh, really? Okay. Yeah. I was like, this is a very niche reference you're making.
So here's just a little summary to remind you what we talked about. My telescopes are in space. I don't know if you know that. Okay, I don't control them, but I get to use big things to look at big objects in space.
Ooh, we're getting votes coming in, but I just want to remind all the people waiting for vote that I'm seeing down to chemical bonds using these microscopes. That is magical. And we're having to use electrons to do this rather than light. The more I talk, the less votes I'm getting. And we're also using a big microscope to look at really tiny things. Like, it just shows how much technology is going into this rather than just having high-tech things to look at big things. We've got 7 votes in and it's 4-3.
I don't know about you. My heart is just like pounding.
Same. This is like the grip Mentimeter has me in.
I think that's it for this one.
Oh, I think we might have to call it there. Yeah, we had 7 people vote in the last round, so yeah, I guess the tables have turned.
Okay. That's good. That's great. Oh, whoa!
Oh! The reaction from both of us is actually like the adrenaline I feel right now. Oh, who is this 8th person that's voted? Like, reveal yourself.
By the way, welcome.
Welcome. Thank you. Oh, should we go into our next 2 rounds of the draw then?
Yeah, I think we might have to.
I think we might also have to let the audience know just how important this is. Not only do we have like our academic integrity on the line, but I might have a forfeit up my sleeve for Affelia if they lose.
I also have a forfeit for Alex as well if she loses.
Amazing, amazing. We'll keep them on tender hooks to see what that is. Should we go on to our second round then?
Yeah, let's do that. So the second round, Pretty pictures round. I think I've got a good chance here because the aurora is pretty, so beautiful. Just look at all of this. You get different colors. You've got swirling, dancing curtains of light above you, and people have like marveled at them for millennia. There are cave paintings depicting of these, people looking at these aurora. There are lots of myths and legends, and they've been in films. And everyone who's seen the aurora just says what an incredible experience it is, and what a life-changing experience it is as well.
I don't want to call you out on something here, Affelia, but I think I have to. I don't know that Jupiter has trees on it. I'm pretty sure these pictures of Earth's aurora, and you study Jupiter's.
Okay, yeah. I just wanted to show off these pictures. But Jupiter's aurora, I think, are much better. They're much bigger, much more powerful than the Earth as well. So this image is to scale. You can see how big Jupiter and its aurora is compared to our planet, and you can fit the whole of the Earth inside of Jupiter's aurora, for example. And even though Jupiter is hundreds of millions of kilometers away from us, you can still get pretty good detail of its aurora. So Hubble lets us see them from the side. And then when Juno flies above the poles, we can see the aurora from above as well. And we can get videos like this one. So again, this is from the Hubble Space Telescope. You can see lots of features. For example, you've got these spots here. There's one there. There's one here moving around. So those spots are caused by the moons around Jupiter. So as they orbit around the planet, those spots move around with them. You can see lots of activity sort of in the polar region here. So the Earth doesn't really have these emissions. It's kind of dark where we are. And even though the cause of these aurora is ice volcanoes, the sun does play a part. So every second, the sun releases a constant stream of charged particles of plasma called a solar wind. And that solar wind can squash Jupiter's magnetic field, and then it can make certain features and certain parts of the aurora brighter. For example, we can see that this arc here is really bright, is really sort of distinct. We've got lots of stuff going on here. You've got like explosions of light happening. You've got arcs forming here. You've got spots as well happening down here. So all of that is telling me that the sun gave out a great big sneeze, and the solar wind was particularly strong at this time. And I can tell that just by looking at this very hypnotic video.
It's very hypnotic. I could sit here and watch it all day, but I do have a question. What aurora did you say this was?
This is the UV aurora.
UV aurora. And you study the X-ray aurora. I think we need to look at that.
Okay, I do have a photo of the X-ray aurora that I took with XMM Newton just last year. So this is a 33-hour-long exposure of Jupiter and its aurora. Are you ready?
I think I am.
Yeah. Ta-da!
I was not ready, I'm sorry. Oh, 33 hours, you said?
33 hours.
Yeah, and there's your name claiming it at the bottom as well. Wow. Yeah. And that was the best you could do?
With XMM Newton, yeah. But there is a good reason. So X-ray telescopes, like XMM Newton, use mirrors to focus the X-rays. And if you were to fire a beam of X-rays directly onto a mirror, they would just pass straight through because they're too energetic. So instead, you've got to place a mirror so that they're almost sort of parallel to the incoming X-rays. So the X-rays come along, they sort of skim off the surface, or they graze off the surface of the mirror like a stone skimming off the surface of water. And XMM has a series of these mirrors. So the X-rays bounce along, and then eventually they're guided onto the detector, which is on the other side of the telescope. I have a challenge for you, actually, Alex. I want to see how good you are at focusing X-rays. I want to see if you have the X-ray factor.
I reckon I can go the wavelengths to really prove myself on this.
Yeah, you rate your aim?
Oh, hugely. Am I not just reflecting confidence to you?
I can see right through your fake confidence.
Oh, okay. Let's swap to the demo cam and you can talk me through my setup.
Okay. So, Alex has a ball of ping pong balls, hopefully, somewhere. Yep. And the mat in front of her there is it's supposed to be the mirror. And then on the other side is a target. There you go. So that is our target. Now, what you have to do is bounce your ping pong ball onto the mat. And it has to bounce at least once and get it into the target, okay? I'm going to give you 30 seconds to see how many you can get in your target. Does that make sense?
Yeah.
Okay, I'm going to just set up the timer. I'm going to give you a countdown. In 3, 2, 1, go. Okay. Keep going. You've got half your time left. 10 seconds. 5, 4, 3, 2, 1, and stop. How many did you get?
1, 2, 3, 4, 5, 6, 7, 8, 9. 9! That's really good.
That is quite good. Well done. I'm impressed. Yeah, good job.
Oh, adrenaline.
So if we go back to the slides, I hope you appreciate my picture a little bit more, Alex.
Only a little bit more.
Oh, okay, it's not so easy to focus X-rays, is it?
No, I think examination actually has quite a hard job.
I feel really blessed actually, because I was the first person to see this picture, and I'm probably like 1 of 6 people in the whole world that understand what's going on as well.
Only 1 in 6.
Yeah,
do you not
quite
want
niche,
to
right?
make it 1 in 7 and tell me, or 1 in 6 plus 9 people that we have watching?
It will be my pleasure. So here, the brighter the pixels, the brighter the X-ray. So we're getting lots of X-rays from this part here, and that is actually Jupiter's northern aurora. The southern aurora, which is the white circle, is not as bright. There are a few explanations. One, the south pole of Jupiter was probably tilting away from us, so we're getting less of its aurora, and also the field strength at the south pole is weaker than it is in the north, and so that can affect how bright the aurora looks as well. Jupiter's atmosphere scatters X-rays from the sun very well as well. So Jupiter here is shown by the green circle, and you can see that it doesn't really stand out from the background, which tells me that it wasn't reflecting a lot of solar X-rays, which meant that the sun wasn't giving out a lot of X-rays. I don't actually worry about how the X-ray aurora look. I'm more interested in the energies of these X-rays, and that's what XMM does really well. It measures these energies very well, and that tells me what causes the aurora, say ice, volcanoes, or the sun. I'm also interested in the behavior of the aurora. So are they bright? Are they dim? Are they steady or pulsing? I'm not interested in how things look. I'm not that shallow.
Not that shallow, just a little bit shallow, but not that shallow. Well, I think the way things look actually really does matter. And hopefully I'm going to prove to everybody that is the case. So I told you earlier that proteins are the tools that cells use to do all of their jobs. Now, if you're anything like me or my parents or some of my friends, you probably have a toolbox somewhere in your house that's slowly collecting up dust in a corner. And there is a reason that in our houses we might have so many tools, and that's because they're really good at doing slightly different jobs. And in cells, it's particularly important. They need to do thousands of different jobs all the time, so they need to have all these tools ready to go. But say I just came back from IKEA and I have some shelves that I want to put up to beautifully decorate my flat. There are a couple different tools I could use to do this, but the way that I would use them changes depending on what they look like. So say, for example, I had a hammer and a screwdriver. These are kind of similar. Like if I just describe them to you, they both have a handle, they both have a metal part, they both interact with things that look a bit like a screw or a nail. But they do this very differently, and that is based on their shape. So the hammer has this like really nice flat edge that hits against the nail and pushes it into the shelving. And the other side is kind of plier shaped, so it can pull things back out again. And this is quite different. That swinging from the air is very different to the way that you use a screwdriver. So we still have a handle, but that metal edge, you really couldn't hit anything with it and actually hit it. Instead, it has a cross shape to fit into the crosshead of a screw, and then you twist it rather than hit with it. And this is really important, the difference in shape and how that affects the way they work, because say, for instance, Affelia and I went in a bit of an argument, and we both wanted to put up shelves, and I gave them all the screwdrivers and kept all the hammers for myself. I could go around every single screw in Aphelia's house and put something in the top of them so they didn't have that cross shape anymore, and they wouldn't be able to do anything. They would never be able to beautifully decorate their flat like mine. So this is really important in biology because say there's a bacteria or a virus or something like that that you want to combat but not affect a human, you really need to get into the shape and how that works. So there's a lot about tools. Let's look at actual proteins. What do they look like? So this is looking at the kind of business end of a membrane integral pyrophosphatase. And I think this is just stunning. So we've got a kind of pink bit in the background and the bluer bit closer to us. These are two parts of the protein that come together to perform its job. And these like spirally noodly parts, these are the actual proteins. And these bits are called alpha helices, which is a pretty cool name, you have to admit. But this glowing part in the middle, each of these like green orbs is a magnesium ion. There are 5 of them here, so we can see down to like ions, which are teeny tiny. Like I cannot express how small this is. And that kind of stick-like shape in the middle, that's a mixture of nitrogens, phosphates, oxygen, all sorts of atoms coming together and forming a molecule that we can see. This is really cool. I have a slightly different image as well. So this is slightly more kind of computer rendered, but we're taking the 3D information and can make beautiful pictures with them. And we can play with textures, we can do all these things because we have 3D objects from microscopes where you might otherwise get 2D ones.
Computer rendered?
Yeah.
What does the original image look like straight out of the microscope?
Oh, okay. Okay, let's have a look at straight out the microscope. So it's a bit black and white, but that's okay. These things are smaller than light, so we can't be expecting there to be much colour in these pictures. But what we are seeing, this kind of light grey part, this is that frozen ice with the protein in it. And each of those kind of speckly, blobby type things is an individual protein frozen in ice, waiting for us to kind of study them and work out what they look like. And as they're frozen in ice, there are all sorts of different like orientations. So if it was me, you might get some that are facing up, some that are facing down, some tilted to the side, pretty much everything. And that lets us build up 2D pictures, which I also have some pictures of. So these look a bit like jellyfish. That's fine, jellyfish are beautiful. And this is really important. These are beautiful. But you can also start to get the detail of what the protein looks like, and we're looking at it from different angles. We're getting this picture that we can build up into a 3D model, which looks a little bit like this. So it's a little bit blobby, but it's beautiful. You can see where the electrons are in this. So all of this like density is electrons. It's really cool. And the different color here shows like how good quality it is. But you can see the strands that will build up into those slightly prettier pictures that I showed you earlier. And I'm not just interested in the 3D shape, I'm also interested in how 4D affects these.
4D, do they like spray water out at you?
It's not quite cinema trips from your childhood. I'm interested in how the fourth dimension or time affects the way that proteins work. So how they change over time, how they move. And I pretty much build up videos to have a look at this. So I've got an example here. The blue swirly whirly bits, this is my membrane integral pyrophosphatase. And those bits flickering in and out, those are individual amino acids and atoms coming together. And that blob, orb, in yellow, that's a sodium ion. And as it comes down to the bottom of the protein, I can see how it interacts with the protein and how it sets the protein up to actually do its job, which is really cool. And I get so much information from this, like how long it takes, what path the sodium takes, where does it interact on its way down to the bottom of the protein, like a huge amount of information. These videos are really cool.
They are cool, but not Oscar worthy.
Maybe not Oscar worthy, but they are Nobel Prize worthy. Nobel Prize 2013 chemistry worthy, in fact.
Okay, bringing out the big guns, and mentioning Nobel Prizes. But remember, I told you some really cool things as well, and I showed you some actual pictures and videos of Jupiter's aurora. Shall we go to the Mentimeter and vote who wins this round?
Yeah, it's nice that you get videos of the aurora, just like I get to make videos of my proteins.
But the aurora is just pretty. You can't deny that. It's really pretty.
But you can't deny that small's pretty either. Look, I've already got a vote. I've already got 2 votes. I've already got 4 votes. Where are the big supporters? Where are they hiding?
Yeah, where are the big supporters? Did you just get your research group to come and watch?
It's actually all my mum. Oh,
yay!
No, oh, we've got 10 people voting now. This is more and more people are joining. It's quite exciting. So the tables have turned, no longer a tie. So 1 round left, unless you think you're going to overtake me suddenly on this one.
Let me just get my I'm joking.
My other phone out.
Yeah, okay, let's call it.
So 1 round left. This actually is kind of a decider, because if I lose the next round, I reckon we both might have to do the forfeit if we've both lost.
Can I be honest?
Ooh.
I don't think you're gonna lose. I think you're gonna win this.
This is the opposite of fighting talk. I don't know how to respond.
Shall we go to the last round then?
Go on.
Okay. So the final round, impact on humanity.
I'm going to be nice and let you go first on this, just because I'm not really sure what studying the aurora gives us other than like pretty screensavers.
So Jupiter's aurora are incredibly powerful, so powerful that they can basically power the whole of civilization. Like if we can harness that energy, would have solved our energy crisis, and we don't have to pay a fortune to light and heat our homes. I think that's pretty cool.
That's really cool. I've actually got my bills due soon. How quickly are you going to get this done?
Depends. How much funding are you going to give me?
That suddenly sounds like it might cost more than Shell.
Yeah, okay, to be honest, it is quite a far way off. But I'll tell you something. The Earth and Jupiter aren't the only planets with aurora. Here are just a few examples. You can see Saturn's here. You can see the ultraviolet aurora here on its north pole. This is Uranus, and these white wispy bits of light there, that's the aurora. Now you might be thinking, why isn't it at the top or at the bottom of the planet? And that's because Uranus is tilted on its side. And so the location of this aurora tells us where its magnetic north and south poles are. And finally, we don't have a planet. We actually have a moon here. That's Ganymede, the largest moon in the solar system. And the one thing that they all have in common here is that they have a global magnetic field. And it's this global magnetic field that accelerates the particles into the atmosphere to give us the aurora. So I've got a video of what happens at the Earth's aurora. The sun here is releasing that constant stream of plasma, the solar wind, out into space. As they flow out to the edge of the solar system, there can be obstacles along the way, like the like the Earth's magnetic field here. So the field lines are in blue. You can see how the solar wind is opening up the Earth's magnetic field lines, and then they get dragged sort of around and behind the planets. That puts quite a lot of pressure actually on the field lines. So the ones on the nighttime side, they get squashed, and then they snap and they reconnect, and that shoots plasma back towards the planet. And then when they enter the atmosphere, they can excite and energize the atoms and molecules in our atmosphere. And when they de-excite, they give off photons of light, and that's how we get the aurora. So the magnetic field, it doesn't just give us auroras, it also protects us from the solar wind, from stripping away our atmosphere. So if we don't have an atmosphere, it would be kind of hard to breathe, and our temperatures would vary wildly between the daytime and the nighttime, and would be exposed to the sun's harmful UV radiation, for example. And that's actually what happened on Mars billions of years ago.
So is it the aurora that will let me live on Jupiter then?
Not quite. It's the magnetic field that makes it more habitable. I mean, I don't think I'd like to live on Jupiter. I don't think it's a good idea for anyone to try and live on Jupiter. But if we see aurora come from a planet or actually an exoplanet, so these are planets orbiting around other stars, then we can say that they're likely to have a magnetic field. And so that would make them a little bit more habitable, and then other astronomers can study them a bit closer, see if they've got the right kind of atmosphere, if they're the right distance away from their star to be not too hot, not too cold. And so studying Jupiter's aurora and understanding how its magnetic field works can help us find out if we're alone in the universe or not. And I like to imagine that there are aliens out there on an alien world looking up at that alien aurora. So I think that's a pretty cool thing to do.
Yeah, that is really nice actually. But I'm just not so interested on people on other planets. I'm interested in the people on this planet. And I think I might be able to win those people over too. So because proteins control so much of our bodies, if they go wrong, that can be linked to diseases. So pretty much every medication, pretty much give or take, targets a protein in some way. So the work I do is really closely linked into medicine. So, for example, the MPPases, or membrane integral pyrophosphatases, that I study, these are really important for the protozoan parasites called malaria, which you might have heard of. And malaria is quite funky. It has this life cycle where it has to go from being in a mosquito to being in the liver to being in blood vessels. And each of those environments are super different. And there's all sorts of different pressures it's under to survive them. And membrane integral pyrophosphatases are what allows it to change from one condition to another and survive it. They're kind of like a pressure stop. So when they change into like a saltier environment, they can help adjust to that, or a watery environment, they can adjust. So what we'd really like to do is to stop MPPases from working, design some kind of medication that would just stop them. And this would stop malaria from doing that life cycle, stop it from being infectious. And that would be really cool. That would be like proper life-saving medication.
So how long are we gonna sort of have to wait to get these life-saving medication?
Kind of similar to your energy harnessing. It's going to be quite a while, maybe like 20 to 30 years. But there is a good reason for that. We want to double check all the data, make sure everything's working properly, make sure it's safe, make sure that the medications do what we actually hope that they're doing. Like, quite a lot of things that have to happen. And it just means there's plenty of work for me to do, right? And just because we're kind of far off making that a reality, that doesn't mean that we're not kind of making science fiction, science non-fiction in other areas. So, for example, when we think about how shape affects function, we can swap those round. So if we know there's a particular job we want a protein to do, we can design one with a particular shape that will do it, which is pretty cool. So for instance, people are designing proteins that can send signals, a bit like in our brains, to use in computers. We're also designing proteins that can collect up microplastics from the ocean, which is really cool because proteins are like biocompatible just by definition pretty much. So not only Is my work going to have impacts on the people on this planet and the people watching? Also technology and the entire planet.
Stealing my votes by mentioning planets.
I'm clutching at straws. I really don't want to have to do a forfeit.
Well, shall we see then? Shall we go to a Mentimeter for the final time today?
Yes. So let's see, who do you think has a bigger impact on humanity? Affelia did make some good points. You know, powerful Aurora definitely use those power civilization, even if they have no idea how to do that. Yeah. Look.
Two votes.
My point always worked for you. Don't forget me. I made some pretty good points. Thank you. I made some good points to everybody. Proteins are what makes our bodies work. They're what we target to make our bodies work better if needed. Even if I'm a little way off having a proper impact.
One of the biggest questions in science is, are we alone? And studying Jupiter's aurora can help us answer that question. I think that's a pretty big impact on humanity there.
I suppose so. Are we alone? Are all those people voting big alone in their viewpoints? Oh, no, wait, another person came through. So 7 people voted. We had 10 people vote in the last round. So that is definitely enough to swing this. Let's see. How are you feeling?
I mean, not so bad. I don't have as many followers as you, so like I wouldn't be as embarrassed.
I am sure that everybody watching and voting has separated any level of popularity from this and is going solely from an objective scientific standpoint that's definitely achievable.
I'm talking about the forfeit that you're gonna have that you're gonna make me do.
Okay. I was going off the popularity contest and the votes. Okay. 7 votes. 1 vote difference. Do you want to call it?
Not really, but I think we have to.
Okay. Oh. We need to decide it quick. Somebody log on. You know what? If this is a draw, we might have to just both do the forfeit then. Let's do it. Okay, so my forfeit for you and your forfeit for me was that we would have to update our Twitter bios to reflect the fact that the other subject was cooler. So I'd have to add bigger, smaller to bigger, smaller. Big is better to mine, and Affelia would have to add that small is better.
I mean, okay, let me stop you there. You won. You won 1 round, and we drew 2. So, although, okay, ignore what I just said. I just won this round.
I'm obsessed. This is how everyone felt counting up the votes last year for the American elections.
Stop the count. Let's both do our full
count. No, okay. Are you settled then? You've won 1. I've won 1. You've definitely won 1. 6 and 4. Okay.
Okay. Shall we? What did you want me to do? I wasn't really listening because I was too too focused on the votes.
So we need to go to Twitter.
Yeah.
You need to go to edit your profile.
Okay.
You need to delete something in there and add in that small is better than big.
Small is better than big. There we go.
And I'm putting PhD student who believes big is better than small. Done.
Cool.
Saved. Well, okay, you know what? That wasn't so bad. It has actually just gone even again.
Well,
we stopped the vote. It's okay. So that wasn't so bad. And I think we both saw your X-ray picture also, so it's not a clean win for either of us.
Yeah, and your raw image from your microscope as well. It's all right. It's okay. I guess that's what you get for studying the invisible, though, right? And like neither of us use instruments that we look through.
No, it's true. And it's actually interesting that even though we're on complete different ends of the scale and size, actually we have an awful lot in common. And, you know, I think we might have even learnt something about arguments today too. Although
And maybe-
mostly that we have an indecisive audience.
And maybe size doesn't matter.
No, it's the equipment you have and how you use it, whether that be a telescope or a microscope.
Yeah, indeed. Indeed.
Thank you very much, everyone, for voting. This has been a lot of fun for us.
That was great. I had so much fun listening and watching your reactions live to like those votes coming in. It was like proper tense.
Genuinely, I've never felt that level of adrenaline in my life.
Thank you both for taking us through that. People learning a lot, well, definitely. I absolutely did throughout. How did you find it? How was that experience?
It was good. My living room is almost as good as the RI lecture theatre where we did our first show. So
yeah, you need to keep on that same sort of level, right? Faraday lecture theatre.
Yeah, we're plateauing.
Yeah. Thank you so much for coming to do this, folks. It's been an absolute pleasure having you here. It's always a pleasure working with both of you. You're both fantastic and just a delight to have. Folks at home, we're not done. There is more to come. So we are fundraising all day today for the RNLI. We're aiming for £1,000. We've got £200 at the moment, so we've got ways to go. So if you can afford to donate, please do that by heading to the link in the banner or scanning the QR codes, and throw whatever you can towards it. The RNLI would highly appreciate it, as would I. We will be back in 2 hours' time for another battle, a wee bit different this time. We're going for big versus little or small today, big and small. And at 5 o'clock, we're going for Wales versus Wales, when the entire ocean will take on the nation of Wales in a comedy panel show. It is going to be absolutely... It's going to be anarchy. And then we're back at 7 o'clock again for another battle, but this time a little bit more bloody, as we go for Science and Sorcery and Dungeons and Dragons over 4 hours for a battle royale. It's going to be so much fun. But otherwise, we're going to sign off now. Thank you, Affelia. Thank you, Alex. It's been a pleasure. Folks at home, if you're watching back later, I hope you've enjoyed it. And the Just Given should still be open if you're watching it back at another time. Take care, folks.